All right. Hello, everyone. Welcome to today's installment of the Corundum developer meeting. Let's go ahead and get into it here. All right. So we got just briefly announcements and then the status updates. All right. So the announcements, well, we're rapidly running out of 2025. So the next developer meeting will be November 5th. The next Switch developer meeting, I don't know what Carlos's schedule is. I'll put TBD for now. But
I think we can make it on 15
the
this
15th.
month. Yeah,
Okay.
October. Yeah,
So 2 weeks from now.
exactly.
Yeah. Okay. All right. Yeah, I guess we got some. I think there was something about the paper, right? We got to do some work on that, maybe.
Yeah, maybe we can have a short meeting, the two of us,
Yeah,
or something. But
and
I
then
have
you've
some
also
ideas
got your
already. I have started working on that.
right, and then you've also got your thesis stuff. So
Yeah, and for that we can also arrange a more general meeting to present something.
yeah, all right. Well, let me know. Let me know what you want to do. Not necessarily now, but we'll figure
Yeah,
that out.
I'm ready to you. Thank you.
All right. Yeah. So next developer meeting will be on November 5th, and then I guess December 3rd, and then we're into 2026 already. Whew, time flies. Okay. So let's go ahead and move on to the status. Let's see. So, over the past month, I've been super busy with this DARPA project, and I have not had time to really do much more versus what was presented last time. So, there are a couple of minor updates, but for the most part, I'm just going to zip through this stuff at pretty quickly because there isn't a whole lot of new stuff here. Right. So, system Verilog system Verilog rewrite process. The idea with Taxi again is to basically take all of the old libraries and render them in System Verilog under the new CERN OHL license, such that if you want to use it for a commercial project, then you can take out a commercial license and get support. So I've got a lot of core stuff transferred over. There's still a bunch of odds and ends that I'm working on, and there's some new stuff that I've added to the library. And then eventually, I guess I have not determined exactly how this is going to work, but the Corundum rewrite is probably going to end up inside the taxi repository as well, just to facilitate, shall we say, cross-pollination between the different components. Um, but that's still somewhat TBD at this point. All right, so moving on to reporting progress. There's a bunch of stuff that I've gotten squared away. AXI, low speed serial stuff, some of the PTP components, 10 and 25 gig max, tri-mode max. To do in the short terms, new IP stack that I'm working on. I need to get the crossbars squared away. I guess I have the adapters on the to-do list. I think what I want to do with the adapters is do some reworking to um, make them a bit more performant. I know the AXI adapter in particular is not particularly great. But I have the old versions basically translated over to System Verilog and in the repository at this point. Um, Maybe it'll be a longer term thing to rework those. DMA and PCIe, working on that. Sync primitives, I have, well, I'm working on some new ones, but the old stuff is ported over and integrated at the moment. Um, yeah, all right. So for the example designs, um, basically I have example designs for the Ethernet subsystems at the moment. Once I get some more PCI Express stuff, I'll probably add some test designs for that. Um, I'm not sure I'm going to have like a comprehensive set of boards for every single subsystem. We'll see about that. But yeah, and I have added some more features to the Ethernet designs. I think I added QSFP or the 6x QSFP28 FMC adapter for the HTG 9200. I should add that for the VC118 as well at some point. And I also added the RFDC core to the ZC111. I think I also have example designs for the ZRF8 boards with the RFDC data converters as well. But didn't put that on this slide. To do Intel parts, I need to figure out how to do the integration on there if I needed a new wrapper or if I'm not going to use a wrapper for those. Haven't had time to sit down and kind of hammer that out. But that is on the to-do list. And then I've had a couple of requests for lattice parts. I also have what is this? An ECP5 5G Versa dev kit. And I might be getting in a Certus Pro NX dev kit some point soon. So I'm going to be looking into that as well. If anybody here is using Lattice parts, might be interested in support on those. Hopefully that'll be coming soon. But more, hopefully, this is a relatively new thing, so I don't have much to say in terms of that at this point because it's still pretty preliminary. Um, all right, so CocoaTB, they're cutting a new release, CocoaTB, and there's a few breaking changes. I think I have most of the code updated at this point. There were a couple of straggler issues. The CocoaTBX Ethernet module, I think, needs a little bit of additional work. Basically, I just need to confirm that that I'm doing everything right because I was getting a scheduler warning or scheduler error under certain circumstances. So I'm not sure if that's like a bug in CocoaTB, a bug in the simulator, or if I'm doing something wrong. It's possible that it's kind of a benign issue, but they just need to downgrade the error to a warning in CocoaTB. I'm not 100% sure about that. I need to revisit that. And once that's resolved, then I'll get a release cut for CocoaTBX Ethernet as well. I've updated, I think, everything except CocoaTBX Ethernet in Taxi, so everything there is running with the latest versions of the test bench code. Right. And I've also done a bunch of stuff to update the Taxi test benches for CocoaTB 2.0. Right now I've been working on the packed versus unpacked arrays in a couple of spots because there's a couple of issues associated with that. A couple of things changed with CocoaTB 2.0 in terms of how the unpacked arrays are handled, which makes sense because they didn't quite work right before. So now they're just dropping support for these particular access patterns. So yeah, I need to make some adjustments to the HDL to correct for that. And this was something I was kind of mulling over doing anyway. Basically, the short story is that in CocoaTB pre 2.0, if you had a packed array of bits, you could slice it up into individual bits and then like await pause edge or neg edge or something. So if you had a clock, for example, on well, I guess the one particular module that's a problem right now is the Ethernet Mac GT wrapper module for ultrascale, and that has clock outputs for the sub channels, right? Because it's got well, it's a wrapper for the quad, so it has up to 4 channels that it contains. Um, and it provides, clock outputs for TX and RX for all of those subchannels. So when I originally built the module, I used packed arrays for most things. I've since realized that maybe that wasn't the best decision if you have those clocks because they are going to separate modules. Maybe it makes more sense to use unpacked arrays. Pre 2.0, you could actually it didn't really matter from the CocoaDB standpoint. You could peel the elements apart and do, basically an await for the rising edge on any of the sub elements. But with CocoaDB 2.0, you can't do that anymore because apparently it didn't work quite right across all the simulators in the previous version of CocoaDB. So basically, I just need to go through those modules and switch everything to unpacked, and then that will hopefully enable CocoaDB to handle things properly. There was also some other bug in the test benches for that Mac module as well. There are a bunch of unpacked arrays in there already for configuration and some other stuff. And some of those are not getting initialized correctly, basically. And I'm not sure if this is a problem in CocoaDB and how it's talking to the simulator, or if it's like a Verilator bug and Verilator's not applying some of these assignments correctly. It's seeming like it's probably a Verilator bug. And I'm not sure if there's really any short-term solution for that, or if we're just going to have to wait for the bug to be fixed in Verilator, and I'll have to implement some sort of a workaround in the meantime. But yeah, that's Slightly annoying simulator related stuff. Um, I also added support for APB to Coco TBX DXI. It's not really related to the 2.0 update, but I got that hammered out and that's now online. And I've also been adding some APB components to Taxi now that this APB support is available in Coco TBX DXI and the CI stuff has been updated in Taxi to use that version. Um, Right. So moving on to Taxi itself, there's been a number of updates there. I've been porting some of the PCI Express components. Right now, I just have the AXI Light Master for UltraScale. I need to get cracking on the DMA stuff. I added a bunch of AXI stuff with converter for AXI and AXI Lite, the AXI Lite adapter, and vice versa, and AXI FIFO. I've added some DMA related um, infrastructure stuff. I've got the DMA RAM and then the interface for that, right? The segmented memory thing. I've also been adding some new modules, right? I got the APB interface, APB RAMs, and AXI Lite APB adapter. And I also added a module for for APB to XFCP, so you can talk to APB stuff directly. Um, the plan with APB is to use that where you need kind of a relatively low performance register interface. So I think what I'm going to do is use it on like the Ethernet um, Mac PCS GT wrapper module for configuring internal stuff and talking to the transceiver channels via DRP, that sort of thing. That's the plan anyway, but might be a little while before I have that fully fleshed out. But at least the code, the infrastructure code is there now. I've also added a couple of additional sample designs recently. So I've got the HTG ZRF8 EM and R2 with RFDC components. I added a ZC111 with the RFDC, and I added the QSFP28 FMC support to the HTG 9200. Those are probably the most notable changes there. All right, so moving on. Okay, the EXI stream slicer. I've talked about this before. The idea is it can pull out a portion of the EXI stream packet and shift things around as necessary. I don't have the shifting logic working properly, so it only works for one byte wide interfaces. Um, but this is something that I've been working on, and hopefully that'll be finished up soon, so it can be used in things like the new network stack for extracting payloads. Not much else to say about that at this point because I haven't had time to work on it in quite a while. Um, but I'm hoping to get that knocked out soon. Um, right, so we've got the Mac Phi and GT wrapper. Not much has changed here, I think, in a while, but this one, it does a better job of integrating the Mac Phi and GT logic all in the same block, such that you can drop it down and simulate the whole thing in a unified way, as opposed to what was done previously, where either some portion of the Mac and Phi logic was sitting at the top level outside of the kind of integration level simulation, um, or well, yeah, it provides a lot of advantages over the previous one. I've talked about this before, so I'm not going to go into too much detail at this point. Um, We are looking at adding support for a bunch of additional stuff to the wrapper now that it's there, including auto negotiation, port splitting, and things like SGMII and USXGMII. Actually, I guess I've come to relearn that USXGMII supports 5G as well, which could be interesting for parts that only have 5 or 6G capable SerDes. Um, so I may look into implementing that. As well. We'll see. Um, and there's also going to be the time stamping and time distribution logic that's going to get looped into this module as well once I get that a little bit more fleshed out. But those are all somewhat longer term things. Okay. I also, well, a while ago added the low latency mode to the MAC-PHY and GT wrapper, which enables running the transceivers in a different configuration that reduces the latency by a handful of nanoseconds. So I don't recommend using it unless you care about, you know, small numbers of nanoseconds because it does increase the area and clock frequencies a little bit. So increased clock frequencies means increased power consumption and more problematic timing closure. So if you need it, you need it, and it's a very very simple thing to turn on and off, just one parameter, which is pretty cool. Um, okay. I also have the 32-bit Mac and PCS. I definitely recommend using that because the area is a lot smaller. I know it's currently tested on ZC106 only. I can't remember if I've tested that on other parts at this point, but I should double check on that. Um, I should probably also update all of the example designs to switch the data width to 32-bit in the 10 gig mode to test this on more boards. But yeah, this one again is just another extension of the existing wrapper, so you can just set one parameter. Actually, I should double check on that. I think it's an I think it's a an extension of the existing wrapper, so you can just change one parameter to switch between the 32-bit and 64-bit versions. Um, yeah, but this is looking pretty good if you don't need a 25 gig support and your part is fast enough to run at like 300 megahertz internally. So yeah, it is a higher frequency, so timing closure is a little bit more difficult, but because the data path width is also narrower, that could be a pretty good trade-off for a lot of cases. Um, yeah, so I did on the KR260, you can see a pretty significant savings, 50% LUT savings, 25% flip-flop savings just with the Mac and PCS core itself. So, um, let's see. Okay, so all of the 10 gig examples were updated for 32-bit, but what I want to do is take everything that has an option for 10 gig or 25 gig to make the 10 gig version use the 32-bit Mac and PCS. So that's on my to-do list. All right. So I've also been doing a bunch of stuff with time synchronization and basically using synckey to do or using the DDMTD logic to do synckey effectively using the GTH, GTY transceivers. So I did a test using the new Mac logic on Corundum. Um, just kind of grafted it together enough to do time synchronization, but not enough to transfer data. Um, and while it works, it's a little bit noisy. So that's going to require probably quite a bit of work to get to the bottom of where that noise is coming from and what to do about it. Um, I've also just very recently did some testing with the Xilinx CMAX, so running at 100 gigabits per second, and basically doing syncing with those. And it's to me it seems a little bit noisier still, but those are also running in well, so I'm not really sure why it would be noisier actually, because they are running in raw mode, not with this buffer bypass logic. So yeah, that's probably going to take some fine tuning to figure out what's going on there as well. Um, but yeah, here's what the 10 gig demo looked like when I put it together a while ago. The 25 gig is basically using the same hardware. 100 gig setup. I don't think I've tried it with two Alveos yet. It was between an Alveo and one of the ZRF8 R2s when I tested it a couple of weeks ago initially. Um, but yeah, I should do a test with two R2s and see how that works. Um, but yeah, with 10 gig, we can very clearly, if I use the delay line to scoot, well, let me go back for a second here. The test setup I used, I had the two Alveo U200s and an optical delay line. So if we step the delay line, we can easily extract steps of just a couple of picoseconds with the 10 gig setup. With 25 gig, because it's noisier, you can't extract all of the steps necessarily. You can definitely pick at a 10 picosecond step, but the smaller ones, not quite as nice. Um, and we're also seeing these temperature dependent steps. So this one was just in loopback, I think with an electrical loopback. So there's no optics, there's no delay line here. This is just running for several hours and we see this spikiness. So um, getting to the bottom of this is yeah, going to be a longer term thing. Um, let's see. So yeah, I've seen these 15 picosecond steps and probably mentioned this before, but there's a presentation from the FPGA Developer Forum earlier this year, which looked at some internal components in the transceivers in terms of how can we directly use the transceivers to recover a frame clock. Um, and they indicated that the delay line that's used on chip for the buffer bypass logic has a 15 picosecond approximately tap size. So that would explain where this 15 picoseconds is coming from. The more important question is there anything that can be done to mitigate that? Not sure at this point. That'll take definitely take some experimentation to try and root that out. Um, right. So I've also been thinking about, how to support multiple link rates on the transceivers, and also be able to do this high precision clocking. So the original idea was to support a bunch of different internal clock frequencies for all the different data rates, but I more recently came to realize that if you do 32-bit 10G and 80-bit 25G, the internal clock frequency is the same. So that could be potentially advantageous. At 25G and at 100G, you can just use this 322 output. Well, so if you're always using the same frequency, then it makes all of the internal logic a lot simpler in terms of how to distribute the timing information across all the ports and how to do all the phase measurements and whatnot. So the idea is that at 25G, um, we may need to do some sort of a basically customized gearbox to convert this 80-bit to 66 bits for the Mac to work correctly. And then obviously we'd probably have to do a gearbox from 32 bits to 66 bits as well. Would that be 32 bits? I guess that would actually be um, you could use the asynchronous or the synchronous gearbox there. Um, in 32-bit mode. You can't use it in 80-bit mode, but you could use it in 32-bit mode. So you wouldn't exactly need a gearbox to go from the 32-bit to 66-bit because this would come out in a format that you could, repack and send that to 66 bits without too much difficulty. But you would need to do something funky at 80 bits for that to work when you're running at 25G. So not 100% sure what the best approach is for this, but it has some promise. Um, yeah, okay, moving on. 100 gig Syncy with the CMAC. So this is something I tested a few weeks ago with the ZRF8R2 and the Alveo U200. We also discovered that the EM board has some signal integrity problems, so didn't do much with that. The PLL successfully, the software PLL loop does lock, but the DDMT output is again a bit noisy. So it seems pretty reasonable if you just plug in a loopback, but as soon as you have the two boards interfacing with each other, it's not super great. So it's also possible that this has something to do with the PLLs on the boards and the clocks not being very stable, or the references not being very stable, but not 100% sure about that. So this is what it looks like. 10 picoseconds is, yeah, it bounds the averaged output, but if we're talking about extracting steps of just a couple of picoseconds, yeah, I'm gonna have to rerun this experiment with now that I'm back with the actual delay line here and see what it looks like. I haven't had a chance to do that yet because I just got back this weekend. But that's at least a somewhat promising start. And then moving on to Corundum itself, the plan is to make a couple of different variants of Corundum to supersede the old one in under the permissive license and written in Verilog. So the new ones will be again under the CERN OHL strongly reciprocal license, and they'll be written in system Verilog. And the plan, at least in the at least that I have at the moment, is to make three different variants. The first one is going to be very small, intended for SoCs, size optimized, supporting a handful of ports at 1 gig, potentially up to, a single port at 10 gig or 25 gig. And then Corundum Lite is supporting, around 100 gigabits per second of aggregate bandwidth, similar in performance to the current version of Corundum. And then Corundum NG is going to be the highest level of performance, ideally supporting up to 400 gig Ethernet. But we'll see about the details on that as things come together. The plan is to use the same driver and the same host interface for everything, and to support basically the same set of core features, including timestamping, checksum, and segmentation offloading. And then obviously, some of these will support things like SRIOV and so on and so forth. So that's that's kind of what I'm looking at here. A little bit more details on each one. Corundum Micro, the idea is to make this a highly size optimized design using basically a micro-coded setup where we can spend a good number of cycles per packet to facilitate transfers, and also to share logic as much as possible between um, all of the ports and all of the directions. So it looks like at 10 cycles, if we can make it work at 10 cycles per packet, if we have four 1 gig ports and we share everything, so TX and RX times four ports at 125 megahertz, that should be able to meet the line rate minimum size, minimum packet size condition. So that would work nicely. If we then totally split the logic out to where we have separate logic handling TX and RX, then I think it should be able to work at 25 gig at if we run it at about 400 megahertz. So unfortunately, that means we won't be able to run all the core logic at the 250 megahertz PCIe clock, because then you won't be able to hit full rate at minimum size for 25 gig. I think that would probably work for 10 gig though. But yeah, at least being able to do this for 1 gig ports and for 10 gig ports, that's pretty good. And we're within spitting distance at 25 gig. This one would support either AXI or PCIe for the host interface, so you can use it on SoCs if you just need a couple of 1 gig ports, or you can use it via PCIe if you want to do something, with TSN, for example, in association with host server or something along those lines. This will support basic NIC offloads, segmentation and checksum offloading, scatter gather DMA, and timestamping. I guess one thing that I'm still trying to figure out is how to properly do like checksum offloads if you don't necessarily have an internal buffer big enough for the entire packet. If we're doing a very size optimized design, we might not want to put all that much block RAM in the design. So if we can't store the whole packet before sending it, then we might need to do something like read the packet twice in order to compute the checksum. So we'll have to figure that one out. But I think there's potentially a couple of options for that. Or the other potential option is that you just don't support checksum offloading if the internal memory is not big enough. I think after discussions a month or two ago, it's going to make sense to have options for multiple queues and scheduling. Originally, I was thinking this is going to be single queue per direction per port, but if you want to do TSN or something, you'll probably want multiple queues. So, okay, well, we'll have an option there so you can turn it on if you want to use multiple queues, or you can turn it off to save resources and save area. And the idea with Corundum Micro is that it's mainly going to be a self-contained core. It's not going to be so much a top-level platform type design. It's just going to be a core you can drop down and integrate into a larger design. And I'm thinking it's also going to be a good method for prototyping the new descriptor format and developing the driver, because it's going to be a lot simpler to build a lower performance design than to try to get everything to run at 1 packet per cycle sort of thing, which is going to require a lot more careful pipelining and such. So start simple, can develop the driver, get a lot of the basic stuff working with this, and then once that's operational, we can move on to the higher performance designs. All right, so Corundum Lite the idea is this is going to be similar in performance to the current design, where it supports around 100 gigabits per second of aggregate throughput, 1 to 4 ports at 10 to 25 gig, something like that. 1 to 2 cycles per packet with the control logic. So for Corundum Lite, we're talking 10 cycles per packet. So you got lots of cycles to do stuff. For Corundum Lite, we're talking 1 to 2 cycles per packet, so we need a lot more pipelining and such to make that work, and probably much more complicated descriptor processing and such. Um, so some of that stuff is at this point rather TBD. This is definitely going to support multiple TX and RX queues and SRIOV, although it's one thing to support SRIOV on the host side. We also need, the network component of SRIOV to actually make something act like like an embedded switch. Otherwise, SRIOV doesn't really work very well. Um, and then I'm thinking this is going to support both PCIe and AXI for the host interface. So again, you can use it um, on SoC boards and whatnot. But long term, it may also support PCIe AXI dual head. So if you have like an MPSoC board with PCIe, then you can share the same network interface between the two, and the ARM cores would effectively have a few PCIe VFs from the standpoint of the host. Um, so that probably discussed this a few times before how that might work, but yeah, the idea is that Corundum Micro is not going to support that, but hopefully we can get that working in Corundum Lite. Um, it might support an application section. We'll see. And it's probably also going to make this, it's probably also going to make sense to have this available as a self-contained core so you can integrate it into a like an SoC type design. So that's that. And then Corundum NG is just turning everything up a couple of notches. So this one is probably going to target the Intel Agilex I R tile. Um, and hopefully it'll be able to support other devices as well. Like I know some Versal devices would probably be a good target for this. Um, and the idea is that this should support, a couple hundred gigabits per second at least aggregate throughput, likely multiple packets per cycle. Um, and I may also look into doing like a multi-headed PCIe because there's definitely some devices that they'll support Gen 5 by 8, but not Gen 5 by 16. Like the some of the newer Versal parts. So to actually get the full throughput, you have to support two PCIe interfaces somehow. So one option obviously is to step and repeat the core, but that may not necessarily be the best option for all of the use cases. And this likely will also support some kind of local AXI DMA for talking to HBM and DRAM, that sort of thing. And the plan is to make this one kind of a platform with the application section and whatnot. Yeah. All right. So that's the different flavors of Corundum. I'm starting to work on the Corundum Micro at this point, but it's definitely going to be a while before we have something minimally functional. Um, I'll certainly keep everybody informed of the progress of that. The other thing I'm working on is the new network stack that I'm calling Zircon. The old stack has a bunch of limitations. Um, so the plan with the new stack is to make it work a little bit more like an operating system level network stack. Although also I need to somehow avoid scope creep so this doesn't get just out of hand in terms of the complexity. Um, but yeah, the idea is that it's going to be a much more flexible replacement for the old stack and supporting IP and UDP natively, but hopefully it also have some sort of a mechanism for supporting protocols like TCP and RDMA that are not just individual packets, but are, have more of a connection orientedness to them. Um, and the plan is to have this operate in kind of a socket style interface so you can make requests to the core to, open a socket, and then you can receive the data that corresponds to that socket. And also have some options to configure, what format that data is in. Do you want all of the headers? Do you just want the payloads, etc.? Um, and it'll be configured both via commands and via register interface. The register interface could potentially change quite a bit depending on the core configuration, but the commands, the idea is that these will be provided over a streaming interface and they will be more independent of the core configuration, which should make it a lot easier to interface with user logic. And then things like ARP, instead of having, a bunch of hard logic for handling that, like in the old stack, that'll be handled by a more compact state machine that can handle multiple protocols. Um, Embedded RDMA is possibly on the roadmap. We'll see about that. And the long-term goal is to take this and integrate it into Corundum, or I don't know necessarily integrate it into Corundum, but at least make it cooperate with Corundum, so you can not only support things like SRIOV and RDMA, TCP offload engines, but also share the stack basically, so you can have some flows handled by hardware through some of the Zircon client ports, and some of the flows handled by Corundum, or everything that isn't handled by hardware handled by Corundum. So um, that's kind of the high level idea. Um, the plan with Zircon is to have these split control and data interfaces facing the clients. And with this setup, the clients can make requests of the stack to do various things, to open connections, to close connections, and also to get notifications about packets being sent or new connections being opened, that sort of thing. And then the data interfaces can be configured to carry packets in various formats. They can either carry the whole packet, or they can carry the packet with the headers cut at a configurable point. So if you just want the payload, you can have that. If you want the whole packet, you can have that. And I'm thinking I may also need to have some intermediate um, configurations um, where there's kind of a restricted set of headers, similar to how like the Xilinx PCIe cores work, where they have their own sort of custom headers that are attached to the packets. It may make sense to do something similar in the Zircon stack when you don't have a connection open, or before you've opened a connection, such that you can actually respond to stuff. Because otherwise, it's a little bit hard to indicate where you want to send a packet if you don't have like a connection context set up. And this is also probably going to be important for internal use with the internal core that's handling things like ARP, because that's probably not going to be connection oriented, right? You just get an ARP request, you get a send a response, and we don't necessarily want the core to have to go, the internal core to have to go and build all the headers. Mainly, it just needs to build the payload and somehow provide the necessary information for the outer headers to be assembled. So that's something I'm still kind of working on, how that's going to fit together. Right. And then for UDP client example, I'm actually thinking there's probably going to be maybe two different ways you can use the stack. One of them is connection oriented, where you can explicitly open a connection. So you can issue a request on the streaming interface to open a connection, specifying the source and destination addresses. And the stack will assign the source port and return the context information. It'll perform the ARP request and all of that. And then once that's done, then you can issue payload data to the TX interface. The stack will build the headers and send the frame on the wire. The other mechanism is to where you can, I need to figure out exactly what the flow is going to be. I don't think you'll have to open an explicit connection, but the idea is that you'll be able to send a packet with these restricted headers, and some information will come from basically a higher layer connection state that basically indicates what the source address and MAC address would be for that packet. And then everything else gets filled in automatically by the stack. So this would enable things like responding to packets without having to have a connection state set up, because that does add some complexity inside the core for managing a new packet coming in. How do we handle setting up the connection state for that? So I guess that's maybe falling more under the UDP server example. With the server, when a request comes in, then the stack will, so what you do is you would issue a request to the stack from the client logic to start listening on a port. The stack would then return the context information about, what ID is associated with that. Then when a packet comes in from the remote host, the stack will set up that connection state internally and provide the payload to the client, along with the connection ID information. And then the client can very easily just turn that data around. But I'm thinking this may be the whole stack managing setting up the connection automatically could be a bit of a problem So it may make more sense to, when a new packet shows up, basically to pass it through with the restricted headers first. And then the client can make a determination of, am I just going to handle it in this format, or am I going to request a connection be opened, which will then reduce the header information. So for some applications, so kind of the way I envision this working is that you might have sort of a multiple client ports, and an initial connection will come into sort of a management port, and that'll figure out, okay, are we going to transfer this over to one of the hardware modules, or are we going to figure out what to do with it, basically. And if it does want to open a connection, then it can open a connection um, to one of the hardware modules, which would then receive the packets without the additional header information. So that's kind of the idea, but it's I'm still getting the details hammered out at this point. But yeah, the idea is that the stack will be responsible for assembling the higher layer headers and computing all the checksums and whatnot. So the user logic doesn't need to handle that. There's I guess, some other wrinkles involving things like VLAN tags that may need to be addressed as well. But that's kind of the high level idea. The status of this stack is I'm working on an initial implementation that's targeting 10G 32-bit. The parser and deparser logic is going to be fixed at 32 bits. For higher rates, we'll use multiple instances that have some striping and destriping logic. For lower rates, we'll do width conversion. So unfortunately, it won't save a lot of logic resources, but it'll use the exact same core, basically. The parser and deparser are mostly complete at this point. I'm working on the data path and rules engine, and kind of iterating on the overall architecture to figure out how everything needs to be connected. So I've kind of done some hacked up data path stuff with a mocked up rules engine, and I'm working on putting together a more fleshed out rules engine. So this thing, it closes timing at 322 megahertz on the KC105. That's pretty good, and it successfully echoes back packets with reconstructed headers. The next step is to actually, make this thing act like a UDP echo server, basically. Um, and that's where I'm starting to run into some of the um, more subtleties of how do you actually manage the stack properly. Um, so hopefully within a few weeks, we'll have this ready for people to start kicking the tires on. um, let's see, what else do we have here? Yeah, so the Zircon, I'm not going to talk too much about the rest of these components here, but the parser, yeah, 32 bits, handles a bunch of different protocols, VLAN tags, IPv4, IPv6, UDP, TCP. Right now at this point, by saying it handles the extension options, it at least figures out how big they are so it can remove them. I don't have a mechanism for actually taking the options and passing them down the stack in a coherent way, or packing options back into packets on the transmit direction. So I'll have to figure that out at some point, because I know there are at least certain TCP options that seem to be commonly used, like the TCP timestamp options. It also computes the whole frame checksum and payload length, L3, L4 header offsets, RSS hash, and validates the IPv4 header checksum. So some of these components are then used by um, subsequent pieces of the stack to extract the payload and things like that. And by having the RSS hash, we can use that for um, um, load balancing. So Corundum had a module for doing that. Well, the parser has to parse the packet anyway. We might as well compute the RSS hash there and then use it later on. This is tested on the KC105 at 322 megahertz. Seems to work fine. The deparser basically does similar stuff in reverse. It can build the packet with VLAN tags, IPv4, IPv6, UDP, TCP. Extension headers and IP TCP options are currently not supported. I'll have to figure that out at some point. This handles IP header and TCP UDP checksums. And it can compute the full packet checksum based on the payload checksum as computed by a different part of the stack. So this has also been tested on the KC105 at 322 megahertz. And the little test design that I put together, this is kind of what it does. It if it receives any packet, so in this case it received an ARP packet, it did parse it as an ARP packet and it extracted the payload from the ARP packet, and then it returned the payload from that ARP packet in an IP frame that it cooked up. So it cooks up the addresses um, and computes all the checksums and everything. So yeah, it's got some signs of life, but it still needs a little bit of work. So I think that's about all I got for today. Yeah. If you have any questions or comments, yeah, go ahead and fire away. Looks like looks like we've lost a few people. So um I don't know if you guys have any questions or comments, but if so, fire away. If not, I guess we'll adjourn for today.
But maybe I can ask something
Yeah, sure.
about the Mac Ham5 wrappers
Yeah.
running at 10. Okay, so the idea is just to move from 64 bits boost width to 32. For that, you also have to double the frequency, right?
Yep.
So for 25G, you are keeping the same interface as before, right?
Well, for 25 gig, well, yeah, basically it gives you the option of if you want to run at 32 bits, then you can. So at 10 gig you can do 32 or 64. At
Mhm.
25 gig, you basically have to do 64 because 32 is going to be over the F max of a bunch of transceiver stuff.
Yeah, that's what I was, yeah, seeing.
Yeah,
Okay.
because at 25 gig you have to run at like 800 megahertz or something. And yeah,
Yeah, that's not gonna work.
yeah, yeah. But
Okay.
ostensibly you could do that if you wanted to. You know, if
Yeah,
you had a
yeah.
fast enough part. Um,
Mhm.
And then I guess something that I have not looked into yet, but you could also use these also at 5G, right? 5G base R, which I was actually trying to figure out recently. Can you even get a 5G base R NIC? I don't know. I've been looking at some of the NICs that I have lying around, and I've been doing some hunting around, seeing if I could get. Does anybody make a Frappin NIC for 5G base R? Doesn't seem like it. Doesn't seem like it. Even like the
I don't think
Mellanox
any.
Knicks. The Mellanox Knicks, they do like 100, 50, 40, 25, 10, 1. I'm like, well, there's a couple speeds between 10 and 1, right? You got 2.5 gig and 5 gig. Where are those? Yeah. What are you gonna do?
Nobody cares about that, maybe.
I guess so. I guess so. But the network tester stuff I have also has a hole there, right? You can do on the SFPs, you can do 25 gig, 10 gig, 1 gig. No 2.5, no 5. It's like, quite annoying.
Yeah.
So I'm like, while some of the stuff would be pretty straightforward to implement, like I need something to test it with so I can confirm that what I have is actually working properly. So yeah,
Yeah, something to
some kind
compare.
of reference implementation of something.
Yeah.
Uh, what are you gonna do? I mean, the nice thing about the 5G base R is that it's 10G base R at half the data rate. So ostensibly, you just change the transceiver configuration and you're done. But
Yeah, you have to check
it'd be
that.
nice if there's a way to validate that. Yeah.
Mm.
Um, I think I have like a 10 gig switch unit with SFPs that I think can do 2.5 gig. I'll have to I'll take another look at that, but I don't think that one can do 5 gig.
You said a
Yeah.
switch?
Yeah, I can't remember where these things, I think it was another eBay purchase. There's a couple of they're not like full rack mount switches. They're like, little desktop switch things with 8 ports probably.
Mm.
Um, yeah. And those things, I know they support 10 gig. I think at least one of them on some of the ports, you can run that at a lower speed, but I can't remember if it was 2.5 gig or 5 gig. I bought it just for a, handful of ports at 10 gig. But then subsequently realized that one of them could run at 2.5 gigs. So I'm like, hey, now I have an option, or now I have a way to actually test some 2.5 gig base X stuff, some kind of
Yeah.
reference device for that. Um, but yeah, for 5 gig, I still haven't found anything, which is annoying.
But if I see any, I'll let you know.
Yeah, that would be good. You can find a whole bunch of 5 gig base T, but I don't want that. I want the 5 gig base R with the SFPs. Ah, Yeah, I
Yeah,
actually
but
bought a Cisco packet switch, a rack mount one, which has a bunch of the NG based T ports that will run at 10 gig, 5 gig, 2.5 gig, 1 gig, 100 meg. Maybe do 10
okay.
meg too? I don't know. Um, but yeah, I figured that would probably be useful for testing stuff. I might have gotten a NIC as well that supports those speeds. Um, although I can't remember where I put it right now. It's got to be around here somewhere. Um, but yeah, again, that's base T. So if you want to connect that to an FPGA, you need, an N base T PHY. I don't have any of those. Yeah, you can get one. Microchip makes an N base T PHY
Hmm.
FMC board, um, which I might have to get at some point, but they're like $800. So yeah,
Well, yeah.
but that would probably be. I mean, that might be good for. Yeah, unfortunately, the Frappin Phi documentation seems to be not available, but potentially that could support both USXGMII and 5G base R. If you can
Okay.
put the Phi in different configurations, that might be the best I can do, right? If you're not going to be doing 5G base R to another computer, maybe you can do 5G base R to a Phi chip and then 5G base T to something else. I don't know. Yeah.
Yeah, yeah. Interesting.
Yeah. But hopefully I can get to the bottom of that because it would be nice to flesh that out as well. Um, And then, yeah, eventually it would be useful to be able to do runtime reconfiguration of the receivers between all these different speeds. Um,
And that'll
but
be
that will
probably,
be, yeah, that'll be a longer term thing.
yeah, a lot of stuff to do or left.
Yeah, yeah, lots of little things that need to be sorted out. It's what are you gonna do? Um,
Because this is now just the two of us. Do you want to discuss some things about the paper now, or do you prefer another day? Mm.
um, well, I guess we could talk about that now. Let me one moment here.